So in today's class, we will see M-array PSK means M-array phase shift key, and under this we will see its constellation and how to design the transmitter of M-array PSK for a designed constellation. So now what we'll do, we'll first look at the constellation, and then based on that constellation we would try to design the M-array transmitter or the transmitter for the M-array PSK signal. So before going to M-array PSK, let's take a quick recap of the QPSK. So this is the polar representation of QPSK signal. Whatever comes out of the QPSK transmitter, the polar representation of that signals look like this, right? If you want, you can just draw it. Root ES is the distance of this signal from the origin, and since all of the signals have equal distance, this you can assume or you can think it as all the symbols, and this symbol is corresponding to signal 1. If you remember, in the very beginning of our lectures I have told you that each signal can be think of as a vector in the vector space or basis function, right? So S1 is this much root ES pi by 4 in phi IT, and root ES, just project this vector to this, and this will give the in phase part and the quadrature phase part. So in general, if you do the same projections, in general any mth signal S1t, S2t, S3t and S4t can be represented as root ES cos 2m minus 1 pi by 4 phi IT plus root ES cosine 2m minus 1 pi by m. Or you can write theta m is 2m minus 1 pi by 4. We are only talking about the QPSK currently, and the duration of this signal is from 0 to 2 TB, right? Because remember, the transmitter, I told you that both in phase signal and quadrature phase signal becomes 2 TB, right? And this complete QPSK signal carries 2-bit information, and therefore the duration of this is 2 TB. So this is the polar representation. You can note it down. ES is the energy. I told you that how to read the constellation. I would put the link again in the description box. That distance square provides the energy of the signal, right? So S1t, S2t, S3t, S4t all are equal energy, and the energy is ES. This we have discussed in the previous lectures. And I also told you how you can look at or alternate way of looking at each QPSK signal. So just go to the transmitter, and according to the possibilities of SIT and SOT, you can write all the possible output of the QPSK transmitter, right? Since I have the quadrature in phase is quadrature phase wala carrier is minus, therefore I am writing minus here. This thing we have discussed in detail in the QPSK transmitter part. So once you write S1t, S2t, S3t and S4t, you can in general write SMT as AC cos 2 pi FCT 2m minus 1 pi by 4. So either you can look at each signal like this or like this. Both are same, just way of representation is different. Here we are not representing this signal in terms of basis functions, but here we are representing each signal in terms of basis function. But physically both are same. This thing we have already discussed, that the AC is root 2 times amplitude of in phase quadrature phase carrier. Just if you, some of you are not yet sure how will we get this from this. So for example, when we transmit 1 0, what happens? For 1, a cos 2 pi fct goes, for 0 minus, for 0 a sin 2 pi fct goes, because minus minus become 1. So you can write plus a cos 2 pi fct plus a sin 2 pi fct for 1 0, and we just multiply by root 2 and divide by root 2. So this, just look at this from here, come to this step. Here cos pi by 4 is 1 by root 2, sin pi by 4 is 1 by root 2. Therefore, you can write this as root 2a cos 2 pi fct minus pi by 4. Further, if you add 2 pi to the argument of cos, it will not change anything, right? Because cos 2 pi plus theta is cos theta, and therefore from this step we get this. So root 2a cos 2 pi fct plus 7 pi by 4. This way you can derive all of these signals. So now we have seen, either you can think of each QPSK signal by this equation or by this equation. This is a better way to see, but it is always good to know that the output of your QPSK transmitter is a signal where information is only embedded in the phase part. That is why it is called phase shift keying, and we call it quadrature because you are all transmitting both in phase and quadrature phase. Okay, you are embedding the information in both I channel and Q channel. So let's discuss a general MPSK signal, right? Here we have only seen this, that there are 4 constellation points. So you are just sending 2 bits at a time and mapping each bit to a vector, which is a equivalent representation of the signal S1T or sorry, it is 1 1, it is 0 0, and so on, right? So can we transmit 3 bits at a time, 4 bits at a time, and so on? So the answer is yes, and we have to go for MPSK constellation in order to do that. So MPSK constellation means, for example, your M is 8, means there are 8 symbols S1, S2, S3, S4, S5, S6, S7, S8. In the constellation diagram, we represent it by a vector, and each represent some signal of the transmitter. So our aim is to design a 8 PSK signal, right? So 0 0 0 0 1 0, there are 8 bits. You have to take input bits, take 3 bits at a time, and you map each of this to some signal which will come out of this transmitter. So since we know that QPSK looked like this, root ES cos 2m minus 1 pi by 4, but now our M is not 4, so we will write it as M. And further, if you remember, I told you that now we are sending 3 bits of information through each signal. Therefore, the duration will be 3 TB, or in general n TB, where n is log 2m. So you can write your MPSK signal as SIT root ES cos 2m minus 1 pi by m phi IT plus root ES sin 2m minus 1 pi by m, and where your phi is same and phi q2 is minus 1 by root TB sin of 2 pi FCT. Clear? So the question is that we put information in the theta I part, right? So is it always true that we take theta I like this 2m minus 1 pi by m, or we can do something else also? So the answer is yes. We can also take our theta I as 2 pi by m. What do I mean by that? If you put, let us take an example of 4 or QPSK, then you can write your signal constellation like this. Put m is equal to 1 and m is equal to 4. The answer is, excuse me, 2 pi m. Or if you write 2 pi m by m, then your m starts with 0 and goes up to m minus 1. So let us take m as 4, capital M as 4. So your m will be 0, 1, 2 and 3. For m is equal to 0, you will have 0 phase. For m is equal to 1, not degrees, it is in radians. So 1 you will have, just replace pi by 2, 3 pi by 2 and pi by 2, pi and 3 pi by 2. Therefore, each of your signal will look like this. Okay. So you can also visualize what would happen in quadrature phase and in phase. You can just break it. You just project each signal in phase part and quadrature part, right? Similarly, if we take m is equal to 8, I told you how to do it. If we take is theta m as this, it should be m. And you can also see what would happen if you take m like this, theta like this. In that scenario, your constellation will look like this. It will start from 0, pi by 4, pi by 2, 3 pi by 4, pi, and so on. So the question is, there are various possibilities of the constellation, and therefore you can map your 3-bit to symbols, right? I told you this is one signal, 62, S3, S4, S5, S6, S7 and S8, and each of these symbol carries the in-phase component and the quadrature phase component. In-phase component is projection of S1 vector over phi it, and quadrature phase component is the projection of all with this vector over the quadrature axis. So the question is how to design a transmitter. Once we have the constellation in our disposal, how can we design a transmitter? So for this we will see the concept of generalized IQ transmitter, in phase quadrature phase transmitter, and it applies to all possible PSK schemes. So what you have to do, you have to first decide the mapping of your signal bits to the symbol. So your bit stream is coming. Now you have to decide what type of mapping, based on the constellation, what bit pattern you want to map to which symbol. So in just arbitrary assignment, you just map 111 with S1, 1010 with S2 and 000 with S8. So what you have to do, once your bit stream is coming like this, you just pass it through a 3-bit or n bits SIPO, serial in parallel out register. So 3-bit would come out, and according to your mapping already decided, you will map your 3-bit to S1 vector. S1 vector has both in phase and quadrature phase. So you will, for example, you want to design a transmitter which will work on this constellation. So what would you do? 111, for example, will be mapped to this. So you will take its in phase component as SI cos pi by 4 and quadrature phase component as SI sin pi by 4. So you will just have a mapping table here and you will map each signal vector to in phase and quadrature phase part. And next, what would you do? Quadrature phase mapping mapped symbol or the component will be sent through phi qt multiplied with phi qt, and the in phase wala will be multiplied with the yit. Oh, in other in the previous example I have taken I here, Q here, so it does not make any difference. You can take either I here or Q here. Okay. So just you can also take I here and Q here if you want, and then you have to map your Q with this and I with this, and just sum them up and we transmit. So once we have this type of transmitter, it is very easy to design the corresponding receiver. What would you do? This is the any MPSK signal which is coming out, and it depends upon the number of symbols or symbol vectors. So if there are 8, so you will take 3 bits at a time. You will map it any of the 8 symbols or 8 vectors, and then this MPSK signal would come out. We multiply it with, again you can write phi it here, phi qt here. Now you have to integrate this over the interval of NTB, right? I told you that you have to integrate it over the time duration over which this signal is present, right? So 0 to NTB, because each MPSK signal is present for NTB duration where n is log to m. So for case of 8 PSK, n will be 3. And next we will sample it at each NTB time, every TB second or every TB time we will sample it. And now we have to put our lambda or the threshold so that you can decide which symbol was transmitted. So from the constellation diagram you have sent either of S1, S2, S3, S4, S5, S6, 8. So it has Q part and in phase part. Again you have to change this. So you will decide what SI hat was transmitted or SQ hat. So SI hat and SQ hat, that you have to decide. And how to take this lambda we know for the case of 2 PSK at least, right? If the constellation is like this, in phase is this, quadrature phase is like this, we know how to choose lambda, right? We have seen it in the class. For higher dimensional, if there are more vectors, then we have to see, but that we don't discuss in your syllabus. But there is a way that we should choose lambda, and therefore we decide which of this component is there, and we call it S1 SI hat and SQ hat. And once we have this SI hat, SQ hat, we will do the reverse mapping from symbol to bit mapping, and then we transmit it through to a parallel in serial out register, and then DK hat will come out. One more point which I might not have discussed, that if you have any in phase and quadrature phase constellation, you can always break it to the quadrature and in phase constellation. What does it mean? It is a ST which is a summation of SIT plus SQT. So each point represent the one of the possible value of the modulated signal, right? So it's a QPSK, so it is sending one of the possible QPSK signal. So what you can do, this is the SIT constellation and this is SQT constellation. Just you have to project all the possible values over I, so you will see that if this is root ES, then you will have root ES by root 2, root ES by root 2, right? See, this is root ES, right? And you know that energy, ES is the energy of ST, which is summation of energies of SIT and SQT. So you can also write this as root E, because ES is 2E, right? So this way you can also see the constellation of in phase separately for the quadrature phase. This is phi QT and this is phi IT. Sorry, this is phi IT and this is phi QT. Thank you.